Welcome to this lecture on methods in biostatistics. Today, we are going to explore a fascinating and crucial topic, type 1 and type 2 errors. Whenever we conduct scientific research, test a new life-saving drug, or diagnose a patient, we rely on statistical tests to make decisions. But what happens when our tests lead us to the wrong conclusion? Understanding these errors is not just about passing a math exam. It is about protecting public health, saving money, and ensuring that scientific discoveries are actually real. Let us dive in and see how we can measure and control these unavoidable risks. To understand statistical errors, let us start with a familiar scenario, a criminal trial. In the justice system, a person is presumed innocent until proven guilty. This presumption is our default starting point. As a judge, you can make two tragic mistakes. First, you might convict an innocent person, sending someone to jail who did absolutely nothing wrong. Second, you might let a guilty person go free, allowing a dangerous criminal back onto the streets. In biostatistics, we face the exact same dilemma when testing a hypothesis. We have a default assumption, and we must be very careful about the types of mistakes we make when deciding whether to reject it. Now that we have our analogy, let us look at the formal statistical terms. In any experiment, we always start with a default assumption, called the null hypothesis, denoted as H0. This usually states that there is no effect, no difference, or no disease present. It is the equivalent of presuming innocence. On the other hand, the alternative hypothesis, denoted as HA, represents what we are actually trying to prove. This could be a new drug working or a disease being present. Our goal in hypothesis testing is to use sample data to decide whether we have enough evidence to reject the null hypothesis in favor of the alternative. Building on our hypotheses, we can now define the two specific errors that can occur. A type 1 error happens when we incorrectly reject a true null hypothesis. This means we claim there is an effect or a difference when none actually exists. In medical testing, this is often called a false positive because the test falsely claims a positive result. Conversely, a type 2 error occurs when we fail to reject a false null hypothesis. This means we miss a real effect or fail to detect a disease that is actually there. This is commonly referred to as a false negative, representing a missed opportunity for discovery or treatment. Why do these definitions matter so much in real life? Understanding these errors is absolutely critical in fields like medicine, pharmacology, and public health. If researchers make a type 1 error while testing a new drug, they might release a useless or potentially harmful medication to the public, falsely believing it cures a disease. This wastes billions of dollars and puts patient lives at risk for absolutely no medical benefit. On the flip side, if they make a type 2 error, they might abandon a highly effective, life-saving drug just because their statistical test failed to detect its benefits. Scientists must carefully balance these risks to protect public safety while allowing medical breakthroughs. Having seen the real-world impact, let us look at how we measure these risks mathematically. In statistics, we cannot completely eliminate the chance of making these errors, but we can control their probabilities. We use the Greek letter alpha to represent the probability of committing a type 1 error. This is also called the level of significance. In this formula, P stands for probability, E1 represents the specific event of making a type 1 error, and alpha is the probability of rejecting the null hypothesis when it is actually true. If a researcher decreases alpha, they make it much harder to reject the null hypothesis, which reduces the chance of a false positive, but introduces a trade-off. Let us apply this formula to a concrete example. Imagine a pharmaceutical company is testing a new blood pressure medication against a placebo. The researchers set their significance level, alpha, to 0.05. What does this actually mean? It means they are willing to accept exactly a 5% probability of committing a type 1 error. In the context of this trial, they have a 5% chance of concluding the drug works and bringing it to market, even though it is actually no better than a sugar pill. Regulatory agencies like the FDA strictly enforce this low alpha value to prevent useless and potentially dangerous drugs from flooding the healthcare system.
Just as we quantified the false positive rate, we must also measure the probability of missing a real effect. This brings us to the type 2 error. We use a different Greek letter, beta, to represent this specific probability. In this equation, P, again, stands for probability. E2 represents the event of making a type 2 error, and beta is the probability of failing to reject the null hypothesis when it is actually false. There's an inverse relationship between alpha and beta in any given study. If you change your test criteria to decrease alpha, the value of beta will naturally increase. This means that avoiding false positives makes you more likely to get false negatives. Let us see how beta plays out in our blood pressure medication example. Suppose the researchers set their acceptable type 2 error rate, beta, to 0.20. This means there is a 20% probability of committing a type 2 error during the study. Even if the drug is genuinely effective at lowering blood pressure, the trial has a 20% chance of failing to show a statistically significant result. If this happens, the company would abandon a perfectly good, life-saving medication due to a false negative conclusion. This represents a massive loss for both the pharmaceutical business and the hypertensive patients who desperately needed a new treatment option. Because missing a true effect is so costly, we calculate a metric called the statistical power of a test. Power is the exact mathematical opposite of a type 2 error. It measures our ability to find the truth when the truth is actually there to be found. The formula for power, denoted by the letter W, is simply 1 minus beta. Here, the number 1 represents 100% probability, and beta is the probability of a type 2 error. As the power increases, the test becomes much better at detecting true effects. A high statistical power is highly desirable in any scientific experiment because it means the study is sensitive enough to discover real breakthroughs. Let us calculate the statistical power for our blood pressure drug trial. We know the researchers set their acceptable beta value to 0.20. To find the power, we use our formula, W equals 1 minus beta. By substituting the given beta value, we calculate 1 minus 0.20, which gives us 0.80. This means that if the new blood pressure drug truly works, the researchers have an 80% chance of successfully detecting its effectiveness. A power of 80% is considered the standard benchmark for a well-designed clinical trial, providing a strong balance between the cost of running the trial and the likelihood of discovery. Now that we understand clinical trials, let us look at how these errors apply to medical diagnostic testing, using conditional probability. When a patient takes a test, the null hypothesis is that they are healthy. Therefore, a type 1 error occurs when a healthy person gets a positive test result. Mathematically, alpha equals the probability of T plus given D minus. Here, T plus represents a positive test result,
and D- indicates the patient is actually disease-free. The vertical bar means given that. So this formula calculates the probability of getting a positive test result given that the patient does not actually have the disease. This is the mathematical reality of a false positive. Let us see the real-world impact of this conditional probability. Imagine a patient comes into a clinic to be tested for a rare viral infection. The patient is actually completely healthy, meaning the condition D- is true. However, the test incorrectly yields a positive result, T+. The test has incorrectly rejected the null hypotheses of health, alarming the patient with a false positive result. What is the physical meaning of this outcome? The consequence is that the patient might undergo immense unnecessary stress, pay for expensive follow-up tests, or even endure harmful medical treatments for a viral infection they do not actually have. We must also define the type 2 error for our diagnostic test. A type 2 error occurs when a sick patient receives a negative test result. Mathematically, beta equals the probability of T- given D+. In this expression, T- represents a negative test result, and D+ indicates that the patient actually has the disease. This formula calculates the probability of the test failing to detect the illness when the illness is truly present. Just like in our drug trial, this false negative rate is a critical metric for evaluating how safe and effective a medical test is for the general public. Let us apply this beta formula to our patient. This time, the patient actually has the rare viral infection, meaning the condition D+ is true. However, the test yields a negative result, T-. The test has failed to reject the null hypothesis, giving the sick patient a false sense of security. The physical consequence here is extremely dangerous. The infected patient will go home untreated. This failure could potentially allow the virus to worsen in their own body or spread to other healthy individuals in the community. In this specific medical case, a type 2 error is likely much more harmful than a type 1 error, so doctors might choose a test with a very low beta. To visualize everything we have learned, let us look at this error matrix. On the top, we have the actual reality. Either the null hypothesis is true or it is false. On the left, we have our test decision. Either we reject the null hypothesis or we fail to reject it. If the null hypothesis is true and we reject it, we land in the red box, a type 1 error or false positive, governed by alpha. If the null hypothesis is false and we fail to reject it, we land in the blue box, a type 2 error or false negative, governed by beta. The white boxes represent correct decisions, including the statistical power in the top right. This matrix perfectly summarizes the balancing act of hypothesis testing. We have covered a lot of ground today, so let us summarize the most important ideas. First, statistical errors are an unavoidable part of hypothesis testing because we are always working with incomplete sample data rather than the entire population. Second, a type 1 error, governed by alpha, is a false positive, where we mistakenly claim an effect exists when it does not. Third, a type 2 error, governed by beta, is a false negative, where we mistakenly miss a real effect that is actually present. Finally, by carefully choosing our alpha and beta values, we can balance the risks of being too gullible versus being too skeptical. You now have the tools to understand how scientific conclusions are made as reliable, accurate, and safe as possible.